great pleasure to have Professor Yuanbo Zhang from Fudan University to give us this physics seminar. So before we start, let me briefly introduce Professor Zhang. So Yuanbo received his bachelor's degree from Peking University in 2000 and a PhD in physics from Columbia in 2006. I think he worked with Philip King at that time. He was then as a Miller Research Fellow at the UC Berkeley. This was actually quite a prestigious fellowship for the top, young talent, towards scientific career. And then he worked as a postdoc research associate at IBM Armaden Research Center from 2010, actually for a few months in 2010, and then joined Fudan University as a professor. His main research interest is on the electronic transport in low-dimensional system, including graphene. He's very famous for his work, the first transport work in black phosphorus. He has been recognized by a number of national and international awards. I will not repeat that now. So we will start to pass the microphone to Professor Yuanbo Zhang. Now, just one last note. Let's do this in a very interactive. Means that if you have questions, please just speak or raise your hand. All right. So Yuanbo, please. Thank you.
Okay. Oh, thank you. Yeah, thanks for your introduction. Let me try to... See everything okay?
Yeah, we can see the screen now.
Thank Xihua for the invitation. So I can talk about the work we did in the past few years. But in general, the general topic is actually is what we think the new opportunities in two-dimensional materials. Of course, the two-dimensional materials now is a big field, but I think still we are just at the beginning of this very big thing. And I will use my work as an examples to show actually there's still much more to do in the future. Okay, so before I move into the 2D materials, let me just go back in history and briefly talk about material in general. So if you go back in the early human history, we found actually that our history are actually defined by materials. So we have Stone Age, Bronze Age, and Iron Age. Well, if you follow this convention and try to define our own age, I think there's no doubt actually we are now living in the Silicon Age. Well, the silicon is the basis for the transistor that we're using everywhere, and it's a foundation of our information society. Well, so the silicon, why silicon is so useful? Because if you make a silicon a thin film in the same film form, and then you can use external perturbations such as a low current or low voltage to adjust its conductance. So its conductance is a semiconductor, so it's between a metal and an insulator. So with a very small perturbation, you can turn on and off almost perfectly. So this was found first in Bell Labs in the 40s last century. So this is actually the basis of the mechanism, the working mechanism of the silicon transistors. So now we know that the silicon transistor is becoming smaller and smaller, and our chips are becoming more and more powerful. So in order to do that, people have to pack more and more silicon transistor on a single wafer, and that makes the single device approaching the atomic limit. Actually, we are now in the nanometer range. So if we want to make the chips smaller or the devices smaller, we have to make it thinner as well. So that cannot go on forever because everything that we are familiar with are made of atoms. So if we so there's a very hard limit in material physics. So we cannot go beyond one single atom. So the ultimate limit would be that we make the material one atom thick. So this is one of the motivations why we study tuning materials. That's also why when graphene just came up in 2004 from Gang Group, there was a much hope that this kind of material could replace silicon as a next generation electronic material and so on. Of course, so far that's not. But this doesn't mean actually this, the 2D material, it's cannot do this because now we know much more about the different materials in this category. Well, so graphene we know actually is probably not good as a semiconductor, but in the past 16 years we have known a lot of new physics in this material. For example, we know that the carriers in graphene is not the carriers we know in conventional semiconductors. The carriers in graphene is best described by Dirac equation, so it's a Dirac formulas in 2 dimensions. So for this reason, it has a pseudo spin and other degrees freedom. So this of course, this is very good for studying the the equivalent of the relativistic carriers, but also because the band structure doesn't have a gap, so that's also why it does not function as a good electronic material. But the real importance for graphene research, I think, is that it opens our mind to a new paradigm. The paradigm is called it's what I call less is different. So if we take graphite, for example, it's a very old material and we have known it for a long time. But if you slim it down to a single atom thick, we have to essentially treat it as a totally different material and has a entirely different electronic structure and optical property, mechanical property, and so on. So apart from graphene, there's thousands of new linear materials that are waiting to be explored, that can be explored in the future. So this was pointed out in 2018 by Monolayer et al. And this materials covers a wide range of physics topics, for example, from semiconductor to magnetic material and to superconductors. And so better yet, a lot of this material can be peeled to few layers just with a raw static. And this been working for this worked well for graphene and also worked well for many other materials. So in the past 16 years, so we have learned a lot of new 2D materials. And at the same time, we also, as a field, have accumulated a lot of experimental techniques. So I think it's about time we can use this the knowledge we accumulated in the field to solve outstanding problems in other branches of condensed matter physics. So here I listed a few such directions. For example, the quantum Hall physics has been traditionally studied in quantum arsenic heterostructures, but now I think the new physics, new compressional quantum Hall physics in graphene has been taking over and been in the forefront of this in this field. And of course, there are new development in 2D magnetism. And in this talk, I will use our work as examples to show that there's opportunities also in topological physics, particularly quantum Hall effect, and also superconductivity, and so on. So let me. So in this talk, I will mainly talk about 2 materials. So first, I will talk about our recent observation of a quantum Hall effect in manganese bismuth telluride 124. And if I have enough time, I'll also talk about our work on high TC superconductivity in monolayer bisco. So let me start with the quantum Hall effect in MBT. Well, so this conventional the conventional Hall effect has a very long history. It's discovered more than 100 years ago. So basically, if you put a 2D electron gas, basically a metal, in a perpendicular magnetic field, and if you run currents through, the electrons will be the trajectory or electron will be bent by the magnetic field by the Lorentz force. So as a result, there's a charge accumulation on the two sides of the sample, and you measure a voltage across the sample, and then you can divide by the current and get a transverse resistance Ry, which is proportional to magnetic field. So this is the conventional Hall effect. And in the 80s, Van Klissen et al. Discovered that if you increase the magnetic field, and if you have a high quality electron gas, and in fact, you see that in certain region of the magnetic, in certain places that you have a quantized, well-quantized Ry. At the same time, RSS go to 0. Indeed, actually, there's a simple way. There's a very hand-waving way to understand this this phenomena. So it goes like this. So this is the 2D electrons moving on the plane. If you have a strong enough magnetic field, the electrons start to go in the orbits. This is called sectoral orbits. So it starts to go in a circle. And for this reason, the electron doesn't conduct anymore in the bulk. So we can take them out with no problem. And it doesn't, so the transport now is wholly entirely carried by the edge state, and this is skipping orbits. So electron always bouncing around and then go from left to right or from right to left. So for this kind of electrons, they don't go backwards on one edge. If they want to go backwards, they have to scatter to the other edge and then go backwards. So this is actually, these states are chiral. So this is the so-called topological states in the quantum Hall effect. And this we call it topological because if you put the local defects, for example, if you put the bulk defect in the middle of the sample, or if you put the edge defect on the side, you see that actually it doesn't affect the fact that actually these states they can also travel from left to right with no problem at all, and they also don't scatter. So that's why if you put two electrodes on one side, no matter how much impurity you have, you always have zero conductance on one side. And so this is a very hand-waving way to understand the quantum Hall effect. Well, so this hand-waving picture can be made precise, and this was done by TKNN. This for people in the 80s. They found actually the sigma xy indeed are quantized. And so is equal square weight times integer, and the integer actually is precise and integer, and it's in fact actually the integration of the Berry curvature on the whole green zone on whole bands basically. And of course for a real device you have edges, and so this integer now corresponds to the number of edge modes that is below the just crossing the Fermi level. So this formalism actually can be made very rigorous and precise. So you see that actually in the previous hand-waving picture, the high magnetic field is very important. It's essential for quantizing electron orbits. But in 1988, Aldin asked interesting question. Can we have this quantum Hall effect with zero magnetic field? It's something impossible, but how do you construct a simple model? I won't go to detail of this model, but in his model, in certain parameter space, indeed, he found that it is possible to have a quantum Hall effect in zero magnetic field. So in principle, it's possible, and this is so-called quantum alarm Hall effect. Well, so how this initial model was too far removed from reality, and it's impossible to realize this model in real materials. But in the last few decades, now through the generations of a few, through the efforts of few generations of theorists, including Nagasa and Zhang et al., now we have a recipe that can produce the zero field quantum Hall effect in real materials. And the recipe goes like this. We start with a three-dimensional topological insulator. Imagine we have a cube, and the 6 surfaces is conducting with it's a gapless edge mode, but the bulk is insulating. Okay, and now next we make the topological material magnetic with the magnetization in z direction. The top and bottom surface now has a gap, and this is induced by the exchange gap. So this the top and bottom surface now are insulating, but the side are still conducting. And the next, we squeeze the three-dimensional topological material, topological insulator into the thin slide, so that only one channel is allowed on the edge. And this edge mode is chiral and is the specialist, and this is exactly the quantum alarm Hall edge state that we're looking for. So with this recipe, we could construct a quantum alarm Hall insulator that can in which we can see the quantum Hall effect at zero magnetic field. So by following this this recipe in 2013, Xue and collaborators found that indeed they can produce a real material that can display this kind of quantization. And what they did actually is that they grow a thin film topological insulator and then dope magnetic atoms into this material and make it magnetic. And indeed, actually, if we do this and make a high quality device, actually, this is exact quantization. And the key here is to break the temperature symmetry with the spontaneous magnetization in the z direction, and that leads to quantum alarm Hall effect in the ferromagnetic topological insulator. So the key is to make the topological insulator ferromagnetic. And now if you look, but now there's a problem. So to make the topological insulator magnetic, we have to dope a lot of these magnetic atoms. Dope enough so that it's become ferromagnetic. But at the same time, these magnetic atoms, they act as impurities in the material. And this is the data taken by In-situ et al. In 2015. And those dots here are the impurities. There are a lot of them because we need enough of these magnetic atoms. So for this reason, actually, we have 2 conflicting demands. So these impurities will at the same time limit the quality of the sample. So that's mean this has been the bottleneck for the study of the quantum alarm Hall effect. And the quantization temperature is limited to 2K in this family of materials. Okay, so ideally, we would like to have a material that has a magnetism, ferromagnetism intrinsically. So that doesn't depend, that we don't need internal doping. And at the same time, it stays as a topological insulator. So this will be the ideal material for this quantum alarm Hall effect. So this sounds too good to be true, but in the past few years, actually, we realized, we as a community realized actually such a material indeed exists. This manganese bismuth telluride 4 is one such material. And so this it's a linear material. And if you look at a monolayer of this material, is actually made of 7 layers of atoms and looks complicated. But this structure is basically just a bismuth 2 terminal 3, which is a typical topological insulator that is integrated by a manganese telluride bilayer. And so this magnet layer will order ferromagnetic within a layer, but between the layers they order antiferromagnetically. So in the bulk form, the material is the antiferromagnetic insulator. But if you slim it down, the material that to outnumbered layers, then because the magnetization is not fully compensated because you have outnumbered layers, now the materials is a ferromagnetic, but at the same time is still a topological insulator. So this is exactly the material we're looking for. So intrinsically magnetic topological insulator that may display this quantum alarm Hall effect, the quantum Hall effect at zero magnetic field. So we start to 2 years ago, we started to peel this material, but quickly we found that this very hard to peel. But and also, if you look around in this field, we found that it's only a handful of known linear materials can be cleaved to monolayer, even though there are thousands of such linear materials around. So the reason is that by peeling these materials, we are basically pressing this thin flakes of the material onto a sticky surface, such as silicon oxide, and then we rely on the thickness of the silicon oxide to peel a monolayer off the bulk. So we very much rely on the thickness of the substrate for this technique to work. Well, the problem is that silicon oxide is not very sticky, and so that it works for graphene and TMD and a few others, but it does not work for majority of linear materials we encounter. So we have to find better ways to peel, and in a sense, actually, this is limiting the progress of the whole field. Well, indeed, such a method exists. So in the past few years, a group has developed developed a slight improvement based on these aluminum oxide, silicon oxide exfoliation technique. So the key is that we found that a thin film of aluminum oxide that are evaporated on the freshly collected bulk is much more sticky than a silicon oxide substrate. So basically, if you evaporate thin film of such material, and then if you peel, and very often this a thin flake, 1 or 2 layers, will stuck on aluminum oxide. And then you can use a complicated method to flip it over and make an electrode, and then you can do transfer. So this is a new method that developed by 3 students, Yuanbo Zhang, Yixin Song, in our group. And this new method can exfoliate these difficult footing materials. And they have tried on a number of linear materials, and they work pretty well. And for example, we work on FGT, MBT, unsternalized, VSE2, and MOS2, titanium sulfide, and so on. And it works very nicely. So for MBT, we could get monolayer and few layers, and we can identify its number of layer in material by looking at the transmittance. And so basically, we could easily identify its layer number. So and lo and behold, so for a 5-layer MBT sample, if the quality is high enough, we could see the quantization of RSY up to 97% of H over E squared at a temperature of 1.4 K, a zero magnetic field. So this is the quantum Hall effect, the quantum Hall effect at zero magnetic field for this magnetic topological insulator. And if you raise the temperature, of course, the effect will be washed away by thermal fluctuation. But we notice that at high field, actually, the quantization more robust. Of course, this is understandable because in high field, actually, we are essentially flipping this antiferromagnetic layers, so that the whole material, all the layers are ordered ferromagnetically in high magnetic field, and that increases the exchange gap for the surface state. And as a result, we have a higher quantization temperature, and the quantization could persist up to 6.5 K under a field of 7.6 Tesla. Okay. So by feeding, how the quantum Lorentz Hall effect disappeared as we increase the temperature. So basically, we take the RSX and plot as a function of 1 over T in the semi-log scale, and so the slope tell us the energy scale of the quantum Lorentz Hall gap. So at the zero field, we obtain a gap of 7.4 K. So this is already a large gap compared to the previous studies. But if we increase the magnetic field, we see that there's jumps as we flip the layers. If we flip the layer one by one, we see a jump every time if we flip a single layer. After 2 jumps, so the 5-layer sample is fully, the spins are fully aligned, and eventually we reach a highest gap value of around 30K. So this is actually a very large gap size in the quantum Hall study. So now let's pause for a second and see what we have done. So basically we take a piece of rock, the MBT crystal, and we peel a thin layer from this crystal and do nothing and just measure its RSY. Okay, and we get a quantized value that are only defined by fundamental constant. In principle, this condition can be precise up to the precision of the traditional quantum Hall effect, that is 1 part in a billion. So just by measuring a piece from a rock, we could probe the fundamental structure of our universe, because our universe, basically the structure of the universe is defined by such a constant. So I think this is a very beautiful illustration of this point to see a world in the grain of science. Well, this is not the whole story. So we actually have a backgate on this device. So we can use the backgate to dope the surface state, which are actually gapped by the Chinchilla interaction. Now we can dope the surface state, and slowly this we can turn. Initially we are in the quantum Anomalous gap, and as we get it to positive gate, and the sample eventually turn into basically a normal metal. Okay, but along the way, you see actually there's something happen around half quantization. There's something will happen over here, and also this show up. This half quantization show up at a two-terminal arc-fact measurement at a certain gate voltage. So there's an additional quantization plateau at the half quantization, half major quantization, and so this can be seen more obviously at the high magnetic field of 14 Tesla as we sweep the gate. So as we increase gate voltage to part of side, and we see actually indeed actually in the middle around around the 0 volt, there's a half integer quantization. So and access go to 0. So that indeed means actually there's an additional quantum Hall state at mu to 2, okay, the fitting factor 2. So basically there are 2 nano levels. So what is this this additional state? So this state actually, again, if you plot the RX at in the two-dimensional plot as a function of both magnetic field and doping and backgate, you see actually this is the mu to -2 state, in addition to the mu to -1 quantum Anomalous Hall state. Okay, over here. So so what is the state? So so there seems to be something more happening over here. So if we take the derivative of RxY, and we see actually the new state actually, there's more states actually show up as lines in this figure. So and mu to 2 state basically is one of these lines actually. So for people working in conventional quantum Hall effect, actually, we immediately realized actually these are actually another levels. Mu to 2 states actually mu to -3, -4 states actually correspond to the Fermi level at different fitting factors. And so now it became clear that the mu to 2 state here, for here actually we have we have 2 edge states, and one of the edge state is contributed by the quantum Anomalous Hall effect, and the other state now is basically contributed by the conventional quantum Hall state. So basically, the surface state in our sample has high enough quality so that the high magnetic field will quantize this quantum the number levels for in the surface state. And we see in the same device, we see both the quantum Anomalous Hall effect and the quantum Hall effect. And so So where do we go from here? So seems like the device now has high enough quality that is comparable to the best MBE samples, magnetic MBE samples. But in the future, because this is the intrinsically magnetic material, in the future, we have hope that actually we could further increase the sample quality and start to see the quantum alarm Hall effect even higher temperatures. Because it has high quality, we can also think of building heterostructures with the quantum alarm Hall insulator and superconductor. And this heterostructure is interesting because the edge modes are believed to be Magellan fermion edge modes. And with this kind of extended Magellan fermions, we could think of break this edge state and create topological qubits. Of course, this is pretty far in the future, but now we think actually now finally we could have a material to reach such a scheme. And our paper has been published earlier this year. And let me point out that the similar works from Yuanbo group in Tsinghua University and Jianwang group in Peking University. So Yuanbo group, they probe basically the even number of layers, and they see as an insulator state, and the Jianwang group probe this high chain number of states in this same field. Okay. Okay. So how much time do I have?
Still have a lot of time. We have half an hour.
Okay, great. So okay, so in the main part of my talk, I will switch my gear and talk about another material, another material family, the high TC materials. So the reason we are interested, we are attracted to this field is because there's a simple observation that is very puzzling. So the observation was that all the layered qubits and also the iron pnictides, they are in the eyes of 2D material people. They are basically 2D material, linear materials, and the basic unit basically is a copper oxide plane in terms of qubit, and also the iron pnictide plane, monolayer iron pnictide plane in the pnictides. So this is puzzling because from textbook we know that by reducing the dimensionality to 2D and 1D, there are more fluctuations. So the fluctuation is not friendly for superconductivity. But why the high TC superconductivity actually appear in such linear materials that basically has 2D or quasi 2D electron structure? This is very counterintuitive. And in fact, actually, I asked this question to experts in the fields and got different answers from different people. So that seemed to me that this is still an open question, even though this observation is very basic and simple. So that got us interested. So we spent 3 or 4 years on this topic. So okay, let me skip this. So our idea is very simple. So basically, we could actually try to get slim it down to 2D and see if it's 2-dimensional or not. If the high TC superconductivity is 2-dimensional or not. Then, of course, this has been thought about and it's been and there are also experiments that have been done on this topic already. Back in the 90s, for example, Cho et al. They stick very large molecules between the physical layers and to separate them. And they found that TC doesn't change much. So, and also there are pioneering work on the growth of heterostructures of oxides that contain just one or a few layers of high TC superconductors. This was done by Boswick group starting from 90s. They also found that the heterostructure remains superconducting at high temperatures. So basically, we know more or less that this material are quite 2-dimensional. But for us, from this 2D material community, so we know that we are aware of this magic tape, the power of magic tape. So we could in principle peel this materials down to one layer and see what happens. And this also has been tried. For example, back in 2005, just when the graphene came after just graphene came up, Gaim group and found that they could peel visco down to a few layers. So there are quite a few groups working on this topic over the years. And most recently, there's a group, Zhang Da et al. In Shanghai, they could peel the visco bismuth 2212 down to half-inch cell and protect with graphene. And they found that the TC decreased as we decrease the thickness. But I question that before we ascribe this the decrease of TC to dimensionality effect, we had to be aware that TC is also a function of doping and a change dramatically with the doping. So if we want to compare TCs, we have to make sure the doping is the same in all these samples. So that's where we come in. So we found that in the last few years, we found that we could make intrinsic monolayers or few layers of bismuth 2212 by intrinsic. What I mean that its doping level doesn't change much as we fabricate the samples. And the trick is that we fabricate at low temperatures, and the low temperature is not very low actually. We could make intrinsic sample. We could freeze the sample at -40°C and mix up our samples quickly, and the doping doesn't change, and then we can prove its intrinsic behavior as we change the as we tune it. So before I move on to this to the data, let me clarify that by monolayer, what we mean is a half-unit cell. So this is actually the full unit cell of the bismuth 2212 is very complicated. But there's actually a one Watt gap between the half-unit cells. So if we peel monolayer, basically we have this unit. It still contains two copper oxide plates. And so with this, with the technique I just described, we could make large pieces of monolayer and put the electrode on top. And this was done by Yi Junyu, Li Guoma, and Peng Cai in the group. And for the first thing we saw that for monolayer of bismuth 2212, even though we only have half-unit cell, it's still a superconductor, and the TC is almost the same as in bulk. Well, we want to compare the TC with the bulk very precisely. But before we do that, we have to be able to tune the TC of the monolayer and compare the optimum TC with the bulk, because we have to make sure the doping level is exactly the same with that in the bulk. So with this in mind, we found that we can anneal the sample very gently in vacuum, and that will decrease the TC slowly. So we could tune the TC, tune the sample from a superconducting phase to the insulating phase. Okay, and if we anneal the sample slightly in ozone atmosphere, we can actually dope the oxygen back. So we can tune the doping up or down. Any way we want. So with this, we could cover a large part of the phase diagram, and this is the superconducting dome, and this is the Mott insulating phase, and this is the strange metal phase. Okay, this is a pretty familiar phase diagram we see in the bark crystals, but now we see the same phase diagram in monolayers. And more importantly, actually, this phase diagram covers the top of the dome, so that we can compare this TC over here with the optimal doped bulk and see if there are any decrease in TC. And we don't find much decrease, in fact. So this is the monolayer TC, the maximum monolayer TC we found in different samples, and the highest TC represents the TC from the best monolayer crystal that we fabricated. And it's within the natural spread of the TC in the bulk, in the optimal doped bulk. So in this sense, we see that has TC in monolayer doesn't decrease. It's comparable, but it's almost the same with the TC, with atom TC in bulk. So by making a monolayer 2212, seems like the TC is not suppressed. Well, the TC is only one parameter. So next, we want to probe the other phases in the phase diagram. And this traditionally was done by scanning probe techniques. So basically scanning tunneling microscope. Unfortunately, we have a scanning tunneling microscope in our group. So we could put the same kind of device in STM, low temperature, UHV, and we can also put a telescope very close to the sample, and we can locate a monolayer inside the chamber. So then we can navigate our tape to the monolayer sample and probe its different phases. So the first thing we found that the topography of monolayer is intact compared with the bulk. So this is the topography of monolayer, and this is the bulk, and the atomic lattice is exactly the same. Of course, there are large scale corrugations. This is because we put the monolayer on top of silicon oxide, which is not exact flat. So basically, it's like a carpet following the curvatures of the substrate, just like a graphene on silicon oxide. Now, next, we probe the different phases in the phase diagram of the monolayer. So, so basically, so we start. So there's a lot of different phases, and these are phases that are very important for understanding the mechanism of activity in cuprates. So we start with the pseudo gap state. So pseudo gap state basically is a soft gap that appear even above the transition temperature, and this is very mysterious. So indeed, so for a optimum doped monolayer, as we reach temperature, we see that there's a gap appear at 110 K, which is well above the TC of around 85 K. So this means that the pseudo gap still exists in monolayer bismuth 2212. Now we go to superconducting phase. In this regime, we probe this phase by limiting our tunneling current within the superconducting gap. And then we look at the interference of the quasi-particles. And now the quasi-particles are perturbative quasi-particle, and they scatter off the impurities on the surface, and they produce a standing wave pattern. And by further transform of the standing wave pattern, we can see where it's being scattered from where to where. And so this is for the high TC activity. We know there's been a very successful octet model. So basically, the firm surface are banana shaped, and the end of banana basically correspond to the highest joint density state. So we can so by looking at this the scattered the standing wave pattern, we could figure out that the quasi-particles are being scattered between these 8 points. So in fact, actually, people have been looking at this, have been able to find all this the 7 peaks, the 7 peaks as correspond to this kind of scattering. So this has been successful in the study of the box surface of bismuth 212 or 201. And in our data, if we do the first transform, we see most of the peaks, except for one, the Q4 is which is too weak to see, but we see all other peaks. So that means actually basically the octet model also described what's happening in monolayer. Well, if we increase, if we change the tunneling energy, we see that actually the peaks are dispersed with the tunneling energy, and from the dispersion of such scattering wave vector of such, we can pipe out the shape of the firm surface. Basically, it's like this, and also the gap function along the firm level along, and it's look like this. Okay, so this basically means actually we are still looking at a D wave superconductor. So basically, the same model that described the bulk surface can also describe a monolayer bismuth 212 in our experiment. So with basically, as far as we can see, there's no difference in terms of the the gap function, and also the shape of the firm surface. Okay, and then the child order phase in hot topic in the high TC community in recent years, and we also see this child order state in bismuth 2212 Monolayer. In the under-doped regime, is most clear, and if we increase the doping, and we find eventually will disappear. Okay, so this behavior and the trend is also inconsistent with what people see in box surface. So finally, you can probe the mod insulator phase, and this phase actually is difficult to probe actually in conventional bulk experiment, because it's difficult to drive out almost all the oxygen and drive the whole sample into the mod phase. But in Monolayer, actually, it's rather it's simplified. The process is simplified because for Monolayer, there's no supply of oxygen from other layers, so we can easily drive out almost all the oxygen by progressively anneal the sample in UHV, in high vacuum, and then eventually will drive into the extremely underdoped regime. So we found that so in this phase, the sample is very homogeneous. So by taking the spectrum at different spots, we see that the spectrum evolved from a mod gap behavior to a pseudo gap behavior. So basically we see the evolution from a mod gap to a pseudo gap, and on a single experiment. So this evolution has been studied in extremely underdoped bismuth 2201 back in the 60s. This was done in Yuan group at Tsinghua University, and if we compare our data with their data, and we see that behavior is almost the same. So this means even the mod phase is not different. It's not so much different from that in the bulk bismuth 221 in the bulk cuprates. So with all the data, we can say that the all essential physics in bismuth 2212 is contained in its Monolayer. So if we are brave, we can even go a step further and say that maybe the high TC superconductivity in bismuth 2212 or even in cuprate family are essentially a 2D phenomenon. And of course, we need to study more of this material and see whether they're indeed correct. But as far as we see in bismuth 2212, actually this seems to be the conclusion. Okay, so now I had described all our experiment, but let me emphasize actually our two experiments basically are examples of the vast opportunities that I see in further exploration of 2D materials. To be specific, I think there are three major directions. So there are still a lot more new 2D material to be discovered. So we have thousands of living material around, and if we can develop better and new exfoliation techniques, we may be able to find new material, new 2D material, and new physics. And as we slim it down to Monolayer or few layers, a lot of these 2D materials are tunable. So for example, even the bismuth 2212, now we can use oxygenation to tune its doping level and study the phase diagram. And additionally, we could use ion gating to further to dope those materials, and we can basically tune it just as we did to semiconductors traditionally. So we could develop new doping methods to tune these materials. And finally, we can stack them up. This is the topic I don't have time to touch upon in this talk. But if we notice that in recent years, there's been a very productive direction, and already quite a few groups found very interesting phenomena just by stacking graphene layers. I believe there's much more to do actually in this direction. So basically, we have more 2D materials to be discovered, and we have stacking. We can stack them together, and possibility basically that endless. So in this sense, I think we're just at the beginning of this field. Okay, so let me summarize. So we see quantum Hall effect in field layer, magnetic topological insulator, MBT, and we also we can also produce a Monolayer basement 212 that retains Hutchison superconductivity. That leads us to suspect that the Hutchison superconductivity is basically a 2D phenomenon. Okay, so finally, let me acknowledge the students. Without students and collaborators, this work will not be possible. So the students who lead the project are Jun Deng, Yiyu, Li Gongma, and Peng Cai, and Meng Zhu from Xianhui Chen Group. And there are people contribute tremendously to the project. For example, Chen Ye and Zhong Xunguo and Yi Shen Song. In our group, and we collaborate very closely with Wang Jin group. So they did a lot of calculation for this project, and our samples are come from a lot of different places. So majority of the samples come from Xianhui Chen group from USTC in China, and the samples are grown by Meng Zhu and Naizhong Wang. We also have get a high quality MBT sample from Zhehan Xu from Carbon Technology in Shenzhen, and we also get a disco sample from Zhongrui Dan, Gugenda Group. We have a national lab in USA, and also from Yasaki Group in Japan. Okay, thank you very much for your attention.
Okay, Yuanbo, thank you so much. That's perfect timing. We still have some time for discussions. We have about 10 minutes. All right, so let's open the floor for discussions. And anyone you want to speak up?
Can I ask a question?
Yeah, go ahead.
Okay, I have a question. I have two questions related to the surface magnetic state or MBT. Is my voice clear?
Yes.
Okay,
yes.
great. Okay, so I know that following your study, by the way, it's excellent talk and beautiful experiment results. I know also following your MBT study, there are odd even number magnetic structure characterizations published, I believe, in Nature Material. However, we know that MBT is slightly different with other layered material because there's no van der Waals gap, or the interlayer coupling is not van der Waals force. Then the question is, now if we look at the surface of MBT, there's doubling bond, or the surface magnetic structure may be influenced by the surface bonds. So I'd like to hear your perspective or opinion about the surface magnetic structure, and possibly how it couple or interact with the bulk AFM property.
I see. Actually, I'm wondering why you think. So you see, actually, there's no there's damping bond. Let me see. From my understanding, actually, so there's a tellurium layer on top and bottom the surface of one monolayer, right? And actually, the bonds of tellurium actually basically saturated. So indeed, actually, there is a van der Waals gap between the layers.
I see.
Yeah, indeed,
Okay.
there's a van der Waals gap. So actually, the sample is more difficult to cleave than graphene, of course. But within the 2D material family, actually, it's rather easy to cleave down to even monolayer.
Okay.
So this also indicates actually there's indeed a van der Waals gap between the layers.
Yeah, I was asking the question because maybe because the van der Waals gap, the interaction is very strong. That makes the material very hard to peel. And also recently there's also a study, they use ARPAS, they found that there is a surface magnetic state. So that's why I would wonder whether this is different with traditional or other layered magnetic material. see.
Yeah, actually, this material, even though it looks simple, but I believe actually there may be much more to it than what we know now. Actually, but from our transport experiment, actually, seems like the magnetism in this material is rather conventional.
I see.
So yeah, so the major, the main features can be explained by simple calculation. I mean, are simple calculations. So this is done by Agribator, Jinwang, and Fudan, and they seem to agree with our observations pretty well.
I see.
And also, so of course there are large body of STM RPS measurement on this material recently, but I think my opinion that right now the sample quality is very important at this stage, so even in our transport sample, if the sample quality is slightly lower, actually, a lot of phenomena is different. So in this sense, actually, so at the moment, actually, I think maybe some of the observations actually are sample specific, sample dependent.
I see.
At this stage. So I think there's a lot to be done actually to improve the sample quality, and maybe a lot of the observations will converge.
Okay. I have another following up questions, technical questions. Is it okay for me to ask?
Oh, of course.
Go ahead.
Okay, it's a following up. So for you in order to peel the MBT, so you utilize the aluminum oxide.
Yes.
So that means aluminum oxide like kind of strongly bond with MBT, a little bit stronger.
Yeah. Yes.
And we also know that aluminum oxide is very active, especially with oxygen. So I wonder, because of the underlying aluminum oxide, do you see influence from it? For example, it modifies the interface property from the aluminum oxide and MBT, or some modification from aluminum oxide?
Yeah, good question. So the short answer is no, we don't know actually. So actually, so far we have no idea. We use aluminum oxide because it works, because they can peel layers very nicely from this material. But whether it will change the bottom surface or will degrade the sample, actually we don't know. I think so. Of course, it has a larger interaction with the sample, so that's why we can peel. But whether this is good or bad, actually, so far we don't know. So ideally, in the future, we could use something that milder, that it can still peel layer, then we can compare. So yeah, unfortunately, we don't know what happened in the interface.
Got it.
Yeah.
Okay, thank you very much.
All right, so do we have further questions?
So,
Yuanbo, I want to ask you a quick one. Justin, you want to say something, right? Go ahead, Justin.
It's just a small question. So thanks for a very nice talk. In your MBT work, you kind of presented these coexisting quantum anomalous Hall state with the quantum Hall states. So some of the filling fractions for the quantum Hall state seem to be 1, for example. So these are fully split in spin already, and so that's split by the AFM order in your system. Is that correct?
You mean split means the spin split, right?
It's spin split already, right? So
yes.
So typically you would expect spin to be degenerate, and so they usually as factors of 2, right, for each new spin split already.
Yes.
Okay, good. A natural question would be how does this coexist? Say if you can push this into a fractional phase.
Yes.
How does this coexist with the quantum anomalous Hall effect?
Yeah, that's a very good question. I also had that question. So I think this, if we go to the fractional feeding, so basically we say a combination of the two edge state, right? Two kind of edge states, the quantum long or quantum long-haul edge state and also fractional quantum pulse edge state. Really, I have no idea. So what happened actually? Yeah, even in this combination of a quantum long-haul and the quantum Hall integer quantum Hall edge state. Actually, there are two kind of different edge state, and actually in principle they are very different, right? So for example, this scale for the quantum Hall effect actually defined by magnetic lengths, right?
Yeah.
But for the quantum Anomalous Hall effect, actually, I'm wondering actually, I'm not sure which characterizes the length scale actually. So, but I'm sure that this length scale is very different from the length scale of the quantum Hall effect.
Mm-hmm.
Yeah. So in this sense, already they are very different. But how they come together, how they coexist on the edge, I have no idea. And you're asking the question of whether the fractional quantum edge state actually will come in.
Yeah,
and then it's even more complicated. Actually, I have no idea what will happen. But it's a very interesting question. Yes.
Yeah, so if say we just stick with the integer side and say you're switching your perpendicular magnetic field in and out of plane, you would expect the normal quantum Hall filling factors to go from 1 to -1, and does this similarly also switch the quantum anomalous Hall as well, and do they switch at the same time? So for example, are you able to get a nu equals to 0 state?
Actually, we tried. We have tried. I didn't show the data. The data was not published, but we tried. Yes, we see signatures of this nu to 0 state.
I see.
Yeah.
And that's because you've counter-propagating quantum Hall plus quantum anomalous Hall?
Yes. Yes. We tried. Yeah, we tried to use oxygen, oxygenation to dope the material very much on the whole side actually. Basically on this diagram. Yeah, on this diagram basically we are doping actually to this side, right?
I see.
And this side actually, here it should be a nu to 0 state, and we see some signatures of that state. Basically.
So what's the signature of that? Is that in thermal transport, or is it like what?
In transport. In transport.
So but that would also mean that you would have no Hall conductivity because it's nu equals to 0, right? So you just have a long toe which has no conductivity. I see.
Basically you're going to see a insulated state, right? But this insulated state actually it's not like other the conventional insulated state in quantum Hall effect. It also has dispersion. In fact, it's very it's a very strange situation, but that's what they expected, and we do see some sort of dispersion actually.
I see. Okay, thanks very much.
Oh, thank you.
Hey, Yuanbo.
Hey.
Very exciting results.
Thanks.
I have one quick technical question. When you mentioned that you do this leaning in ozone, does it suggest that if you do it in vacuum, you actually lose oxygen?
Yes. Yes.
Okay.
Yeah, actually, that's exactly what happened. Actually, we can decrease the doping. We can lower the doping level just by leaning in vacuum.
Mm-hmm. Okay. Okay. Now, another thing is that the monolayer sample has roughly, equivalent critical temperature and superconductivity compared to bulk samples. So I think that also means that, in principle, any pairing mechanism towards the superconductivity remains robust in monolayer. Is that right?
Yeah, should be. Yes.
Should be. Okay.
Yeah, should be. Yeah. If any model that requires a 3-dimensional coupling, then our data will just show otherwise. Yeah.
Mm-hmm. I think this. I remember Professor Qikun Xue's group some time ago. They use MBE to grow this. I remember it's a half layer, right? It's a half unit cell.
Yes. Their sample is also it's also 2-dimensional. But our monolayer actually is a complete monolayer.
Complete monolayer.
Yeah, because it has all the surrounding oxide, bismuth oxide planes all in there. But their monolayer basically, is less than it's not a complete layer. Basically, they get rid of actually the strontium oxide or bismuth oxide and just expose the copper oxide. Yeah. So in this sense, actually, our the two samples are very are completely different. Oh.
Hello.
Hello. Can you hear me?
Yeah, I can. I think it's
oh.
Okay.
Can you hear me now?
Hello.
Hello. Oh, I think it's breaking up.
I can hear you.
Oh, okay. Can you hear me now?
Yeah.
Okay. Finally. Yeah. But
sorry. It's my internet problem.
Yeah.
Do you have new questions? All right. If we do not have anything further, please join me. Thank Professor Yuanbo Zhang for the exciting talk. Thank you, Yuanbo.
Oh, thank you.
Thank you so much. Thank you.
Thank you.